Hey everybody, it's linear algebra with me time. Today we're going to talk about how to find eigenvalues. Last time we talked about what an eigenvalue was, what an eigenvector was, but we can't really find an eigenvalue, so we can't find an eigenvector yet per se. So let's start off. We're going to recall that lambda is an eigenvalue for A if we have this equation right here where matrix times vector equals scalar times vector for the same vector, and it's not 0. And then through some little manipulations, we get down to this equation right here. So what this last equation gives us is we have a matrix equation with a non-trivial solution. And that's important because it's a homogeneous matrix equation. So non-trivial means what? You mean we've got AX equals 0 has non-trivial solutions. Let's run back to IMT. What does that mean? Means that our matrix isn't invertible. So this entire thing right here is our matrix in question. So that would be the traditional A, and then V is taking the place of X. So we're going to apply what we know to the A minus lambda I, since that is the whole matrix now. So that means A minus lambda I is not invertible. And from last time, we got a cool fact about non-invertible matrices. We learned that the determinant of these guys is going to be 0. So not invertible means 0 determinant. Like, okay, now we're getting somewhere. So then to find the lambdas, we just need to solve this determinant equal to 0 thing. So we'll say solve that for lambda. You might be like, what? It makes a lot more sense in action. You're just like, how am I supposed to solve that? Let's go ahead, let's do an example. So we talked about how 4 is an eigenvalue for this particular matrix. We're going to verify it using the determinant method that I just talked about. So we want to take the determinant of A minus lambda I. Remember, that means we've got 2, negative 2, negative 2, 2. I'm going to put my matrix. Remember, these bars mean that I'm taking a determinant. I'm going to just do that for shortcut notation. So then when we add those matrices together, now we can just say 2 minus lambda, negative 2, negative 2, 2 minus lambda. And while we know how to take this determinant, right, we multiply across. So 2 minus lambda, 2 minus lambda, and then we subtract and multiply across again, negative 2, negative 2. There we go. So that's our determinant. And then I can simplify this a little bit. This is going to be 4 minus 4 lambda, lambda squared, minus 4. Lambda squared minus 4 lambda. But the important part was what? What did I say on the last page? Determinant equals 0. Okay, so I said the determinant was equal to 0. If lambda is an eigenvalue, that causes the determinant to be equal to 0. And so in the end, you find the determinant and then you take this and set it equal to 0. You're like, oh, this is a thing that I can solve. I can find lambda now. So then lambda equals 0, lambda equals 4. So, yep, there we go. There's our 4 eigenvalue. And we also got an extra one. That's cool. Now we have all the eigenvalues for A. Let's run through another one. Let's run through a bigger one. Here we go. It's basically just turning the crank because you already learned determinants. You should be comfortable, hopefully, with that by now. Let's turn a crank in a very tedious manner. Maybe even try pausing it and turning the crank on your own and then fast forwarding and seeing if you got it right. Okay. There's no easy or obvious thing to expand across, so I'm just going to go with the top row plus minus plus for the determinant. Then we have 4 minus lambda. Okay, so that's one term, and then we have minus a -1. And then, just in case you're uncomfortable, forgotten, remember you cross out the row and column he's in, and then you do the determinant of the 2x2 matrix that's left behind. Next one is going to be a 6. 6, that's okay. So then I am sure that nobody wants to see me sit around and multiply and combine like terms. So I'm just going to tell you, trust me. Okay, and then how do I know that? I use Mathematica. Feel free to use Mathematica to write this out, prove to me that you know how to take a determinant, but feel free to put that into Mathematica or something to make it multiply it out for you, because that's kind of a waste of your time. Okay, so now what? Now we need to factor this. We've got this equals 0. We've got to somehow factor this. Oh, I didn't write the hint in here. Hint. 1 eval is lambda equals 2. And honestly, I would not expect you to factor this without some sort of hint like that. What does that give us? It means we know that we can write the factorization like this. So then the question is, well, what's that something and how do we find it? Do you guys remember polynomial long division? If not, here's a refresher. So we've got lambda minus 2 is going to go into negative lambda cubed plus 13 lambda squared minus 40 lambda plus 36. So this is why we made you learn how to factor and do polynomial division all the way back in the day so long ago. So remember, the goal is to match the coefficient here. We're going to do negative lambda squared, because when you multiply that here, you get negative lambda cubed. See, now they match. Minus, which turns into a plus 2 lambda squared. And then just like normal division, or normal long division, you take the thing that you multiply by, and you subtract it off. So here we go. Now we have 11. And then we bring the next number down, which in our case is an entire term. Okay, and then now we repeat. Now we want to match this 11 lambda squared. So plus 11 lambda. So that's 11 lambda squared. Minus 22 lambda. Subtract that off, get a negative 18 lambda, bring down the 36. So minus 18 lambda plus 36. Excellent. So when we subtract it off, we get 0. So then lambda minus 2 times, what is it? Lambda squared plus 11 lambda minus 18 is going to equal 0. And then that factors, you get lambda minus 2. And then can pull, I think pulling a negative out to the front for this is way easier to think about. So I pulled the negative out, and then I can see that it's going to be this. Nope. It's not a plus, it's a minus. There we go. So then lambda equals 2 and 9 with multiplicity 2 for the lambda equals 2. And it's very common notation to write them out separately because, believe me, you need both of those lambdas. When you get to a place in that the sad thing is we won't necessarily hit this in this class where we have to apply it to some really cool problems, but if you do something like differential equations, you end up using this whole eigenvalue thing to find solution to systems of differential equations. And you need both of these eigenvalues, and you're going to need both of their eigenvectors, which are going to be different, and we'll cover that in a sec. So just, you kind of have to accept this one on faith for right now, that knowing, keep in the back of the mind, you need to know what its eigenvalues are and what their multiplicities are. Okay, so beyond that, notice we got this special little polynomial. We can even back up to right here. This was the I would say the most simple form of the polynomial where we worked to get the vector formed, but it was a polynomial with lambda as your variable. And since we're mathematicians, we have, of course, named it. We call the polynomial that we get when you take the determinant of this guy, or we call the polynomial equation, the characteristic equation. And then the name of just the determinant of A, so without the 0, not the equation, just the determinant, that's the characteristic polynomial. You saw that. When we took the determinant, we got a polynomial. And then we're going to have as many multiplications as we are entries in A, like column and row wise. And that means we're going to end up multiplying lambda together n times. And so you end up with a degree n polynomial, which makes sense because last time we had A was 3 by 3 and we got a degree 3 polynomial. And that meant we got 3 answers. They weren't unique answers, but we got 3 answers. Okay, so if lambda is an eigenvalue of A, we say lambda has multiplicity k. If it has multiplicity k in the characteristic polynomial, you guys should be familiar with the term multiplicity from before. Nothing much has changed. Okay, so now we're going to suppose we have an 8 by 8 matrix and they give us the characteristic polynomial. Can we find the eigenvalues of A and give their multiplicities and be like, yeah, that's like a piece of cake. So lambda equals 0, which has multiplicity 2, from, or nope, that's cubed sitting there. Okay. And then lambda equals, let's see, from this part we'll get a -7, multiplicity 2. And then the next part is going to be lambda equals 1. And that has multiplicity 1. And then the last one is lambda equals -1, multiplicity 2. And then if we add these up, that's 2, 3, 4, 5, 8. Cool. So I'm at least being consistent. So how do we find eigenvectors when you have an eigenvalue of multiplicity 2 or higher? Like, it's the same thing. Like we saw, you do the a minus lambda, and you actually plug the number in and you solve for the vector, you solve the system. Like, what do you mean? Will they have the same eigenvalue? Like, can they be different? They can be different. And in fact, you want them to be different. You want them to be linearly independent. Let me show you how this pans out. So we know how to find the eigenvalues for this matrix A. In fact, I think, yeah. Okay, sorry, I just had to check. So from example 3, we know that lambda equals 2, 2, and 9. So we don't have to redo that, thank goodness. Oh. Now what we want to do is we want to do the convention, by the way, is since you end up with a finite number of them, is to label them lambda sub 1. That way you can say v sub 1 is its eigenvector, and you can see which eigenvalue and which eigenvector match up. Okay. So that's why there's a little sub 1 on here. Moving on, we know how to find the eigenvector. So let's go ahead. We're going to solve the augmented matrix A minus lambda I 0, because that's equivalent to solving A v lambda v. Quick reminder. So then this is going to be equal to, and that's going to be a 4 minus 9, 2, 2, -1, 1 minus 9, -1, 6, 6, 8 minus 9, 0, 0. So I've got the steps down for you guys in case you did want to see them, but I don't think you really want to sit there and watch me do Gaussian elimination forever. So now we've solved the augmented matrix. That means we're down to interpreting it. We have V3 is free, so V1 is going to equal V3. V2 will equal V3 as well. So then V equals 1, 1, 1 times V3. That is our solution set. So then to get an eigenvector for our eigenvalue, you just pick something. I'm going to say let V3 equal 1. You do not pick V3 equals 0. Okay. And then here we go. This is the eigenvector. Notice this is the step that I put the little sub 1 on our vector. That's because he now is the eigenvector I've chosen to correspond with our lambda 1. Also, just going to point out this V1 and this V1 are very, very different. One is an entry in the vector, and the other one is a vector as indicated by the hat. There is no correlation. I'm going to turn around in the next problem, and I'm going to use V1 to indicate the first entry again. but that is not going to be our v1 vector because now we're going to start talking about a different lambda. Okay. So here we go. If it makes you feel better, you can like solve for x and do like x1, x2, x3, and then reserve the v stuff for after you've picked your eigenvalue or eigenvector, just if it helps you with notation. Okay, so next one, we're going to do lambda 2, but also 3 is equal to 2. That means now we have to solve the AV equals 2V, and then that's going to look like the augmented matrix A minus 2 I with zeros. So then if we plug that all in, you get 2, negative 1, 6, 2, negative 1, 6. So this is easy, thankfully. So R2 minus R1, R3 minus R1, 2, negative 1, 6, and then everything else died. Okay. So then V1 equals 1/2 V2 minus 3 V3. So then V is going to equal 1/2 V2 minus 3 V3, V2, V3. And then we can separate this into two vectors, the V2 vector and the V3 vector. Okay, from our knowledge of null space, we know that this guy and this guy form the basis for the null space. That means that they are linearly independent. So what we can do is, since I already told you we want linearly independent choices for lambda 2 equals 2 and lambda 3 equals 2, we want them to have different linearly independent eigenvectors. So if we do let V2 equal, I'm going to say 2 because I don't want to deal with the 1/2. But it's okay to let V3 be 0 because you've already got other stuff to make it not 0. Then V2 with the vector hat is going to be 1, 2, 0, like that. And then lambda 3, I'm going to do it the opposite. This time I'm going to let V2 be 0 and V3 equal 1. Let's see. So again, here we go. V3 with the hat is different than V3 here. V2 with the hat is different than V2 here. There is no correlation between the two of them. That is why it is very important when you're doing like your homeworks and stuff to write things with a hat, because maybe you're not talking about things with a hat. Okay. And again, if I were to ask you a problem, like on an exam, I would say pick two linearly independent eigenvectors for lambda if you have a multiplicity of 2 for your eigenvalues. But you're going to have to accept me on faith when I say that is a very important thing later on. But that's all I have on characteristic polynomial. It's not really anything too new, like this last little bit about choosing linearly independent eigenvectors was a little bit new. But the rest of it, we've done determinants. We've done polynomial factorization a long, long time ago. I will ask you to go through the polynomial division in all of its full terrible glory on the exam, and then I will never ask you to do that again. You may use Mathematica to factor things and stuff, but I do want to make you guys go through it. So homework 3, do it the hard way. Builds character. But that's all for now. I'll see you probably before too long. Bye.